before I move on to this picture, at the bottom of one page back, on the bottom of the 50, page 50, we're talking about pulmonary ventilation and alveolar ventilation. We talked about I'm getting a sore throat, so excuse me if I got a little hoarse here. But we talked about forced expiratory volume, okay, and obstructive and restrictive diseases. Do you guys understand the difference between that, or you want me to go over it again? I did this morning. Okay. So I had a little bit more time with you on Tuesday, so I wasn't sure if we've gotten through that. So obstructive and restrictive pulmonary diseases, I draw on this little picture where this is normal. All right, showing the conducting system and the alveolus. Then in obstructive, we have a narrow conducting system and a normal volume, okay? And so with this narrow airway, we have a decreased FEV1. The amount of air that you can blow out rapidly and forcefully in 1 second is low, less than 80 to 84%, okay? However, the airway, the total lung capacity is normal or larger than normal. In fact, you often have increased residual volume. And that's because you can't blow all the air out, and it just keeps staying in there and causing your lungs to expand. Okay? So diseases like this were asthma, emphysema, or just a whole group of disorders known as COPD or chronic obstructive pulmonary disease. Okay? If we look at that the graph, all right, where we forcefully blow out to vital capacity, and at 1 second, we measure, this would be forced vital capacity, the total volume we can blow out, and at 1 second, that would be the FEV1, okay? And so if we divide that by the forced vital capacity, we get a percentile, which is greater than 80 to 84% in a normal individual. Okay? So if we look at the fact that we have a higher residual volume, usually a normal total lung, vital capacity, then someone with obstructive pulmonary disease would have a lower FEV1, but would eventually be able to reach a normal forced vital capacity. It would take them longer, all right? But they would have a normal total air that they blew out of their lungs. So their FEV1 would be lower, okay? Because their FVC is normal, then their percentile would be less than 80%. So that's how this test would reflect. Is that clear? Okay, because it takes them so long that at 1 second they haven't blown out as much, but eventually they can blow out the same volume because they haven't lost volume space. It's the airway that's narrow. With restrictive, they have a normal airway, but for some reason they've lost access to, or the alveoli have been filled up with fluid. So this can happen with pneumonia, pulmonary edema. That's where it fills up with fluid with those two, okay? Or some type of tuberculosis or tumor or some disease that blocks off the airway. So in this case, they would have the key thing here is that they would have a decreased, it may or may not be force, it doesn't have to be measured that way, but they would have a decreased vital capacity. So they would have a less, overall lower lung volume. So if we were to look at this graph for them, here's normal, all right? So with restrictive, we eventually reached a normal vital capacity. With restrictive, and I'm exaggerating this, it would look like this, all right? Where their vital capacity is lower, but at 1 second, their FEV1 is still greater than 80%. Does that make sense? I've kind of exaggerated that they would probably have a vital capacity of greater than 2, but the overall volume is low, but they don't have a problem expiring or inspiring, okay? So the FEV1 would be normal, but their all vital capacity would be low. Yes?
So they would just have to breathe more often? Like,
Or be on supplemental oxygen if it's pneumonia and we don't even have access to any airways. We need to increase the concentration gradient to get greater access to that. Okay? So before we move on to external respiration, I wanted to finish pulmonary ventilation by talking about the volumes of pulmonary ventilation. This is at the bottom of page 50. And compare that with what actual alveolar ventilation refers to. Alrighty. So can I erase this board?
1 second.
You with that? Okay. So remember the formula for cardiac output? It was a mechanism of determining the overall blood volume that was pumped out of the heart in 1 minute. And so it was stroke volume times heart rate. So the volume of each ventricular contraction times the number of contractions in a minute. So we have a very similar formula for respiratory volume, all right? Rather than how much blood is pumped out of the heart in a minute, how much air is breathed into or out of the lungs. So it should be the same volume, all right? So the number of times you breathe is your respiratory rate. And what would the volume of each breath be identified as? What would it be, what's the name of the volume of each breath? I heard it. Tidal volume, okay? So instead of saying stroke volume times respiratory rate, pulmonary ventilation is tidal volume times, stroke volume times heart rate. Respiratory pulmonary ventilation is tidal volume times respiratory rate, or the other way around. Doesn't really matter. Okay? Are you done with the board?
Yeah.
Almost? Okay? So pulmonary ventilation is equal to respiratory rate times tidal volume. Average respiratory rate is 12 breaths a minute. Average tidal volume is 500 mils. And so this comes to an average of 6,000 mils in a minute. Okay? Now, that's the air moving into the lungs and or out of the lungs. But not all of that air has actually reached the alveolar respiratory membrane. Remember we talked about conducting zone and respiratory zone. The respiratory zone was where we actually had gas exchange occurring. So we have the conducting zone and we have the respiratory zone. The conducting zone region is also known as anatomical dead space. That air is not available for gas exchange, and so we have to subtract it from the tidal volume to get the volume of air that actually reaches the alveoli. And it's approximately 150 mils. It's going to vary from person to person, but that would be average or standard. So now alveolar ventilation is equal to respiratory rate times tidal volume minus 150. Okay, so if we take this formula, 500 times 300 and 500 minus 150 is 350, and that comes to, I believe, 4250. It's in the table on the next page, on page 52. $4,200. So it's not, it's a good amount. Now, let's change the character of our breathing, okay? So if we breathe very rapidly, but more shallow, the anatomical dead space becomes a greater proportion of each breath, all right? So if we increase our respiratory rate to 20 breaths a minute, all right? And we decrease our tidal volume to 300. Our pulmonary ventilation is still going to be 6,000 mils, all right? However, if we subtract 150 from 300, we've decreased our alveolar ventilation to 3,000, even though we have the same amount of pulmonary ventilation. Okay? Or, let's breathe really shallow. So if we increase our respiratory rate to 40 and decrease our tidal volume to 150, it's still, pulmonary ventilation is the same. 150 minus 150 is 0. Alveolar ventilation is 0, even though we're breathing 40 times a minute. What we're doing is moving air in and out of our throat. So it's much more effective if you're trying to get more oxygen down into the alveoli, rather than increasing respiratory rate, to decrease the respiratory rate and increase the tidal volume, all right? So in that chart, respiratory rate is decreased to 5, tidal volume is increased to 1,200, which those of you that tried out this spirometer, it's not that difficult. And we still have a pulmonary ventilation rate of 6,000. Okay? Decrease respiratory rate to 5. Now notice when we subtract 150 from 1,200, it's a smaller proportion of that overall volume of gas. Therefore, a greater amount of each breath is actually getting down into the lungs. So I think it's 5250, am I right on the table?
Yes.
So we actually have a greater, even though we have fewer breaths, we actually have a greater alveolar ventilation than with our average normal breathing rate and normal tidal volume. You're going to actually have a greater proportion of each breath flushing into the alveoli. Okay. All right. So now let's look at external respiration. Pulmonary, remember there were 3 phases of respiration. Pulmonary ventilation is just the movement of air into the lungs and out of the lungs, okay? And so that's what we were talking about by changing the pressure, moving the diaphragm and the muscles, and atmospheric pressure pushing gas into the alveoli. So now we're going to look at external respiration. And external respiration is the gas exchange that occurs from the alveolus into the pulmonary capillary, and across the respiratory membrane. So these would be a series of type 1 alveolar cells, creating the simple squamous epithelium. And I don't have my red pen, but then we would have our pulmonary capillary with its simple squamous epithelium and a small amount of connective tissue in between. And that is our respiratory membrane. So what are the gases that we find in our alveoli? So on Tuesday, we were talking about atmospheric pressure. And atmospheric pressure at sea level is 760 millimeters of mercury, okay? Air is a mixture of gases. So not quite 80, almost 80, 78, 79% of air is nitrogen. About 20.9% of air is oxygen. So approximately 21% of atmospheric pressure is going to be oxygen. And that equals 159, we'll round it up, 160 millimeters of mercury. Okay? So this is what we call the partial pressure, all right? The mixture of gases, and that proportion of the pressure of the gas, the number of molecules creating the force of the gas and caused by oxygen, is 21%. This does not change as we go up in altitude. So if you were to go up to Tahoe or Denver, the atmospheric pressure would be lower, but it would still be 21% oxygen. Okay? If you were going to go down to Death Valley and be, whatever, 1 atmosphere lower, it'd still be 21%. You'd have more gas molecules, you'd have more oxygen, but it'd still be 21% because you'd have more nitrogen and more carbon dioxide and everything else. All right? So that's what we mean by a partial pressure. Now, when you breathe this air in, yes?
Sorry. So, what they say when you climb, like say those mountain climbers that climb, Mount Everest.
Yeah.
Aren't oxygen molecules, they're a lot less at that altitude?
There are fewer of them.
But they're still at 21%.
Correct.
Because
So there's a lot less of everything because of the gravitational force has decreased. So I'm going to show you a graph.
So the percentage stays the same, but the amount in the enclosed area is.
Right. So it's this graph that I have in here, because sometimes I talk about high altitude diseases, so I'll just go ahead and move to this. This is a confusing graph because it talks about percent, and the percent is changing. So, but notice at sea level, it says 100% oxygen. Our air is not 100% oxygen. So that gives you a clue right there. But if we consider 160 millimeters of mercury pressure to be 100%, all right, then if we move up to Mount Everest, 29,000 feet, that's at 30%. So we would take a third of 160 millimeters. So we would have about 50 something, 55 millimeters of mercury of oxygen. So that's how you would interpret that, but still 21% of the overall available. So it's the pressure of oxygen decreases, but its proportion of the mixture stays the same, okay? Now when that gets into the lungs, it's not 160 because we have carbon dioxide diffusing out of the blood into the alveoli, all right? So in the lungs, our partial pressure of oxygen at the alveolar level has decreased to 104. Now I think I have these numbers flipped around. So on page 54, where it says external respiration, partial pressure, and the alveolar oxygen partial pressure should be 104, and the venous oxygen pressure should be 40. So those two numbers on page 54 are flipped. So obviously, now when oxygen, here is a gas, all right? And as a gas, it will pass between the phospholipid molecules of the membranes of our cells, and will move into the blood, to the plasma. And it becomes soluble in the plasma. So it has solubility to cross the lipid, it has to be soluble in the lipid membrane, and it has to be soluble in the plasma, okay? So this solubility is a mathematical formula of its size and solubility in the fluid. And so, for instance, carbon dioxide is 20% more soluble than oxygen. Not 20%, 20 times more soluble than oxygen is. And you'll see how the numbers change for that. But oxygen is a higher concentration here, PO2. Now it says venous blood. So remember, this venous blood is coming from the veins in the body. It's brought to the lungs by arteries. So it's pulmonary arteries becoming capillaries, but it's the venous blood of the body. So you kind of have to keep that in the back of your mind. So the PO2 of blood, venous blood in our capillaries, is equal to 40 millimeters of mercury. That's the gradient that is driving the gas out of the alveolar air sac and into the plasma of the blood. So it'll cross the respiratory membrane and start to dissolve into amongst the water molecules of the blood. Okay, so we'll have in the blood, we'll have 21% of the gases in the blood will be oxygen. Almost 80% of gases in the air is nitrogen. We have nitrogen in our blood as well. Is anybody a scuba diver? I'm certified, but I haven't been since 1993. So I probably would have to get recertified. So when you scuba dive, you breathe air out of an air tank. It's not pure oxygen. It is under pressure. The reason for that is for every 30 feet that you dive, atmospheric pressure increases by 1 atmosphere, and that squeezes your lungs, so it's difficult to expand them. So you're not going to get very much air in, okay? So you breathe in pressurized air, which is compressed. It's been squeezed too, so you can still take in an adequate number of air oxygen molecules. Now you're taking in compressed nitrogen, so the nitrogen molecules are closer together too. So you're taking in more nitrogen. And that's why, depending on how far you go down and how long you've been under and how much time the gas has to become solubilized in your plasma, you have to moderate and be aware of how fast you move to the surface. So for a Christmas present, I got my husband, the first Christmas we were married, a course in scuba diving. I took a 6-week course through the YMCA at the college I was teaching at in Tennessee, and his was a PADI course. It was 2 long weekends. I'm certified to dive to 100 feet, and he's certified to dive to 60 feet. But I would never go to 100 feet without him, obviously. it took him until October to get up the courage to take his scuba diving class. And he kept saying, well, what happens if, and what happens if that, and what happens if I'm sitting at the bottom of the pool and I lose my mask or I lose my oxygen tank? I said, honey, you're 12 feet. You stand up 5 feet from the surface. I mean, no, not quite. You know, just go to the top. Well, what if I'm in the ocean and I'm 40 feet? I said, honey, people free dive down farther than that. I said, you just swim to the surface. Now, you only need to be careful if you're breathing, you know, the compressed air for an extended period of time. And at 40 feet, it takes hours, almost hours and hours, for that to be a problem. And so he said that he learned the most taking this scuba course, learning to control his fear. Because he would start to panic just sitting on the bottom of the pool. And his heart rate would start to go up. And he'd just have to look up and go, okay, it's really not that far away. I could reach up in my hands, you know. And that was learning to how to process his fear of that he learned the most of. And so he got certified down in Monterey. And he said the weirdest part of it was, well, the hardest part was the fact that his Farmer Johnson fit and he got flooded with icy cold water. But the weirdest part was it all got stirred up with the silt, and this is all flowing at him, and he's like, I can't breathe this stuff. There's all this dirt, you know, I can't breathe. It's like, okay, I'm not breathing the dirt, I'm breathing the air that's in my, you know, mouthpiece. So to celebrate that summer, we went down to the Caribbean, and every day his gas use would decrease by about 200 pounds of, well, I don't know, whatever the pound of pressure, but anyway, you could see a market. So the first day we had to leave 5 minutes early because he had to reach the, you know, not the bottom, but the danger level of pressure in his air tank, and we had to service and get back on the boat 5 minutes before anybody else did, because he'd used up, he's a big guy, and he'd used up with his, and by the end of the week, you know, we were down there as long as everybody else with plenty of air to spare. But the thing is, with that higher pressure, you're driving more gas in if you come up too fast from an extended time. So my checkout time was in Florida. We went straight down a 100-foot well, deep spring well, and sat on a log and took our mask off and put it back on, and you know, came up to the surface with a buddy and all that kind of stuff. And so you have to then stop at pre-described depths and wait for your system to equilibrate at the lower pressure. So if you come up too high, the gas actually comes out of solution and forms gas bubbles in your blood, and most of it's nitrogen because that's 80%, and that can create problems in joints and cause pulmonary embolisms and stuff. So there's a whole physiology science that you're taught briefly when you do scuba diving. So this is dissolving in the fluid of the blood, and is going to be affected by, you know, the temperature of the blood, by a variety of components of the blood in this particular set of gas exchange. So the colder the temperature, the more solubility there is going to be, and the hotter the temperature, the less. So where would you expect to have the greater biomass? In the Arctic Ocean or down in the Caribbean where Steve and I were scuba diving? In the Arctic Ocean. Now most people, before I tell them the temperature factor, will go, oh, they think of all the coral and the fish, and my husband and I saw a huge turtle and sea snakes. We turned in 2 dives for a one-night dive. And it's all colorful and tropical. But in the Arctic, you have tons of plankton, the tiny little microscopic, well, they're not microscopic, you shed a light at night and you can see them floating around, and the total biomass is greater. So I always bring up the subject, I've never been to a party where people had ice cubes that had flowers in them, okay? But if you went to some fancy English tea or whatever, or wedding reception, certain flower petals are edible, nasturtiums, pansies, violets, candied violets, you know, they used to decorate cookies and stuff. And so if you wanted to pretty up the water, you could freeze these flowers in your ice trays. Most of our ice comes out rather cloudy. All right, so what would you do? There's no point in having a flower in there if you can't see it. So how do you get clear ice? What do you think, based on what we just got through talking about? Boil it first. Exactly, because it comes out of the tap all kind of cloudy anyway, but the oxygen that's been added to it as it's kind of, you know, tumbled out of the tap, And so you boil it, that increases the energy of the gases that are dissolved in it, dries them out, and then freeze it, and it's going to be a clearer ice product because it's not going to have that dissolved gas in it when it's frozen. Well, we don't exactly go freezing our bodies to get more oxygen soluble in our blood, but it does have a relationship when we talk about how oxygen comes off of the hemoglobin. What activity increases body temperature? Everything that we do, we should do every day. I don't know how many of us do. Exercise, all right? And obviously when we exercise, we need more oxygen. So the higher temperature makes it easier for the oxygen to move through the blood and out into the tissues with that higher energy component. All right, so if you'll turn to page 54, when we talk about this external respiration, we talked about diffusion. I didn't have you guys in Bio 430, but I know you talked about diffusion and osmosis and filtration and mechanisms by which molecules move across the membrane. So one of the factors that affects this is the concentration gradient or pressure gradient, same thing, okay? So that's what I've shown on the board for oxygen. The concentration or pressure gradient is 104 to 40. And that's going to drive oxygen as a net direction of diffusion from the alveoli into the blood. All right? There'll be a small amount that will move back out again, but the net amount is moving into the plasma of the blood. Okay? Another factor of diffusion is distance. Because diffusion is caused by the random motion of particles bumping into each other. So the greater concentration we have, the greater the force with which they bump into each other. So diffusion, if we have a gas, at the highest concentration of that gas, diffusion is going to cause them to start dispersing. And what happens? Does the rate stay the same as the gas diffuses away from the central area?
No.
Concentration is going to be less here, so it's going to start slowing down. The good thing about breathing is we're constantly refreshing. That, because a student asked me this morning, well, how can the blood equilibrate at 104 and be equal to the alveolar air? Wouldn't it be half of that? Wouldn't you have 52 in the alveolus and 52 in the blood? And she had a good point, except for the fact that we're constantly refreshing the alveoli. And this blood is not static. It's flowing by this alveolus, and then it's flowing by another alveolus. So it starts out at 40, gets to another one, and maybe it's 50. Would it be diffusing at the same rate if my PO2 is 90? PO2 is 90, and it gets to 104? No, it's going to have to slow down, but it would still have a difference. And will it ever be more? Will this ever be 110 if this is 104? No. So the highest it can get is an equal amount. Okay? But now let's say that my diffusion is increased. I have pulmonary fibrosis, or I have pneumonia, and I've got an exudate, a fluid exudate, that's separating that. That's going to slow down the rate of my diffusion because it has a longer distance to travel through. So how could I increase the amount of oxygen that's diffusing into my plasma if I have a greater distance to travel?
Temperature.
Yeah, it's a little hard to make the lungs cold though. Or hot. A nasal cannula. Let me change my oxygen I'm breathing, increase the concentration, increase my alveolar PO2 to 110 or 120 or 150, and that's going to increase the concentration gradient and move the oxygen faster so that even though it's going a greater distance, I'm going to end up with a better amount than if I had the normal concentration gradient. So instead of doing this, I'm going to do this, and therefore drive more oxygen into the membrane.
Sorry,
It's
I
okay.
just didn't hear what you first said. I'm sorry, maybe what
Okay,
she said.
so with a greater distance,
I understood the concept, but what did you call it?
A nasal cannula?
a nasal cannula,
Cannula?
or a mask.
Oh.
So if you're going to go to the hospital, they'll have oxygen access pipes to the wall around near the beds, and tubing from that either as a mask or as two prongs that go over the ears and into the nose. That's the cannula. the mask fits right over, okay? So it becomes a mixture of regular air and also the solubility. So here's where we talk about the difference with carbon dioxide and oxygen, is how fast it goes across. But those are the three factors that are most effective, of course, in our total area. So with emphysema, we start losing the alveolar walls. They break down, and we have really large air sacs instead of lots of smaller ones. So we lose the surface area. So it takes longer because we don't have as much surface area for that exchange to occur. Okay? All right, so with this transport, I'm not ready for that yet. What happens? I've drawn this big red blood cell in there. Remember, red blood cells are almost the diameter of a capillary, so that there's not much more distance that the oxygen has to travel once it gets into the blood to get into here. So if we eliminated the red blood cell, our plasma would have a PO2 of 104. All right, as it carried that blood back to the heart and got pumped to the body. That amount of oxygen, plasma with enough oxygen solubilized in it to reach that arterial pressure, is insufficient to keep your body alive. Okay? You need the oxygen that's transported on the iron as well. So if you have a hemoglobin of only 2 grams per 100 liters, or deciliters, that's not enough to keep, you would be lying in bed probably dying. With 5 or 6, you're too exhausted to walk a half a mile. Okay? So most of the oxygen, oxygen is carried in two pathways, 2 mechanisms. One is dissolved in the blood, all right? And the other is bound to hemoglobin. So oxygen transport is just dissolved in the plasma. And we measure that as PO2, partial pressure of oxygen. And it usually has a little sub-signal, arterial or venous or ATM for atmospheric, to talk about where this has been tested. And the second method by which we transport, and by far the greater volume, is bound to hemoglobin. So without hemoglobin, with insufficient red blood cells, we don't have enough oxygen. Okay? So let's take a look at that. Hemoglobin, remember, is made up of 2 chains. We didn't talk a lot about them, but we have alpha and beta chains. And those 2 chains create a molecule that kind of shifts back and forth in shape, depending on whether oxygen is bound to them. And each alpha and each beta chain has incorporated into it an iron atom. And that's what oxygen actually binds to. All right? So I'm going to draw a cross, not because it's a cross, but because it has 4 ends. And iron that represents the hemoglobin molecule with 4 binding sites for oxygen. All right? So as oxygen moves out of the alveolus and into the plasma, it doesn't stay in the plasma. As the numbers get higher, this oxygen is going to leave the plasma and move into and bind to my hemoglobin. When it does so, that creates room in the plasma for another oxygen molecule to move in. All right? So when the best scenario is that when the blood is on its way back to the heart, all of the hemoglobin iron ions have bound to oxygen. We have 100% saturation. And we've equilibrated the solubility of the oxygen with the alveoli, and our PO2 is at least 100, okay, 104. That's the maximum amount of oxygen that the blood can carry. When the hemoglobin is saturated, the plasma is equilibrated with alveolar. All right? Now, what if I wanted to carry more oxygen? What 2 different things could I do if I wanted to get more oxygen in the blood? I can increase my oxygen concentration, can breathe, pure oxygen. Is that going to add more oxygen to my hemoglobin?
No.
No, because it's already saturated. So what that will do is it will increase my PO2, okay? So what separate thing could I do to increase my oxygen transport? Increase the number of hemoglobin molecules. Take vitamin B12 or EPO, which is a hormone that the kidneys make to increase red blood cell synthesis. Move to a higher altitude. Stay there for 6 months, and my body will make more red blood cells. Okay? And then when I move back down to Sacramento, I'll be able to run twice as fast. I'd have the endurance. I'm not sure if I'd have the muscle effectiveness. So the only way I could increase hemoglobin transport would be to add more hemoglobin if I was already saturated. All right, so now let's look at the physiology of this hemoglobin transport. So, do you guys understand the chemical meaning of the word affinity? We've used it off and on. So it's talking about the chemical attraction between two atoms and the creation of a chemical molecular bond. If those two atoms have low affinity for each other, they will bind for a shorter period of time or not at all, if they have none. But if they do bind to each other and create a chemical bond but with low affinity, that will be of short duration and that bond will be easily broken and they'll come apart. Okay? If one atom has a high affinity for another, then that's a bond is a strong bond and it will stay, the two atoms will be associated with each other for a longer period of time. All right? Hemoglobin is unique in that its affinity for iron, it's the affinity for iron within the hemoglobin is changing depending on environmental conditions. The pH, whether carbon dioxide is actually bound to hemoglobin or not, because that changes the shape of the hemoglobin. So at first, the hemoglobin affinity attraction, chemical attraction for oxygen is low. So when the first oxygen molecule binds to hemoglobin, it doesn't stay there very long, all right? Even when the second one binds, it takes that second one binding to increase the affinity for oxygen. So after that second oxygen molecule binds, the third one and the fourth one bind much more readily and will stay there, okay? So what do we need to do if those first and second oxygen molecules, let's say here's the first oxygen molecule, moves into the red blood cell, binds to the iron atom, and then boom, a split second later, it's gone again. What happened to my saturation? I want that oxygen to stay there. So what do I need to do to get that oxygen to stay there? Let's say we're playing a game of musical chairs, all right? And I've got 5 chairs, we moved all the tables out, I've got 5 chairs in the room, and about 10 5-year-olds, okay? So we're playing a game of musical chairs, only we've changed the situation a little bit. Instead of having a regular chair, we've taken a metal chair and tilted it slightly so the seat's like this, and then we rubbed grease on it, olive oil. So when they sit down, what happens? They slide right off again, okay? Very little affinity between that kid and that chair, all right? They didn't stay on there very long. So I've got these 5 kids running around and the music stops, they jump on their chairs and they slide right off again. Now, what if I had 50 kids? And as soon as one kid slid off, there were 3 more kids to try to sit on that chair. And even if they all slid off, there would be more times when there was a bottom on that chair than if I only had 5 kids, okay? So, if I try to get oxygen to interact with my iron atom in my hemoglobin, the more oxygen I have around, the greater the likelihood that there will be one on there at any given time, or maybe 2. And when I have 2, the easier it will be, the flatter that chair becomes, and even if it's slippery, the person's going to sit there, the easier it will be for the 3rd and 4th oxygen molecules to stay on there, all right? So that's the effect of having a high PO2 is it ensures that even if this with this low affinity, at any given time, if that one comes off, right away there'll be another one there. And I don't care which one is there, as long as I have an oxygen molecule there. And now that makes it easier for this one and this one to stay, and now all of them are going to be there longer. Okay? So that's the interaction between PO2, which is just our word for how much oxygen is dissolved in the blood, and hemoglobin saturation. All right? So now, as this oxygen then is building up in here, increasing concentration, some of that will come in here, and the more that does, the more likelihood I am to actually get more oxygen bound to my hemoglobin. And when they all have oxygen, it's saturated. Okay? Now, if I'm at a high altitude, as we saw in that chart of the mountain elevations, I'm not going to have a high enough PO2 to get saturation. I might only have 1 or 2 on my hemoglobin because I'm at that higher altitude. And I'm not going to run around with an oxygen tank when I'm only 25, which I'm not, but if I was, okay? Even at my age, if I'm living in Mexico City, I'm not going to run around with an oxygen tank. So what does the body do? If each hemoglobin can only carry 1 or 2 or 3 oxygen molecules, because there's not enough to completely saturate it, part of acclimatization is make more hemoglobin. Okay? So let's say that each hemoglobin, and this is a severe case, let's say that each hemoglobin molecule only can carry 2, but if I have twice as many red blood cells, twice the amount of hemoglobin, then I'm still carrying the same amount of oxygen. Okay? So the body makes more red blood cells. During those 4 to 6 months it takes to acclimate to a higher altitude, that's one of the things that's happening. There's also changes in heart force and blood vessels and stuff, but that's one of the major things that changes is more red blood cells are synthesized. So when you move back to Sacramento for a few months, you're going to have all this, another form of natural blood doping. You're going to have all this extra blood that's able to carry all this extra oxygen, and you're going to have all that extra energy.
Would that be illegal if you were in the Olympics, or say?
People do go and train at high altitude. So when the Olympics were in Mexico City, and I'm not sure what the actual ins and outs are. I mean, I don't know how that you prove that you went, I suppose you could show that you went and trained. People would, there's Olympic training sites in Denver. People would go to Mexico City several months earlier. When you have the Tour de France and they're climbing in the Alps, they'll do other races and train in other mountains to not just get the practice of riding up and down a mountain, but getting the acclimatization.
So would they be able to tell like the difference between artificial blood doping and the altitude? You know what I mean? Like if they were to inject.
I don't know if they would, because EPO is banned. EPO is the erythropoietin that the kidneys produce. So as an artificial stimulant, it's banned. But that's what your body makes. That's why you make more red blood cells. The kidneys are making additional erythropoietin. I don't know the specifics of any particular sport as to how much. Maybe it's the percentage. You can only increase your viscosity of your blood, or maybe it's since they like numbers, you know, you can only increase your hemoglobin up to a certain level, and any more than that is considered artificial. Maybe one of the ways in which they go about that. Okay? So then in reverse, all right, we want the oxygen to come off. Doesn't do you any good to have your hemoglobin saturated